Well, howdy! So I'd like to look at, in this problem-solving format, something that has to do with the sail bogey. Okay, the sail bogey is an object, is a trolley that runs on a rail, like that, and it is driven by a sail. The reason why I love this is because it's one of these things that proves whatever idea I get, no matter how stupid it is, somebody's used it for real as an actual method of propulsion. So sometimes because of necessity, and sometimes for conservation purposes, like in World War I, a sail bogey was used in Britain to run supplies up and down the docks. These things actually existed, and I probably have made another video. This is the first one that I'm making on it, but I probably have by now made another video that has something to do with the sail bogey. And so you've looked at it once or twice. So there are a couple of things that I could do that have to do with the sail bogey, and I'm not sure which ones I'll do. In this particular case, what I'd like to do is show a wind force that is not conservative. I should have a companion video to this one, and that companion video will explain how this is a non-conservative force, and therefore you can't have a potential energy. And that's going to happen because along the path that we're going to show here, and if we look at this down here, the path that we're going to look at is going to be a curved path along a curve like that. Hopefully a better circle than that one. And our sail bogey is going to travel along the path in the tangential direction, because that's what the tangential direction is the direction of travel along a path. And then the wind is going to be going up on the left side of the screen and down on the right side of the screen. Talk a little bit more about that in a second. So as you're going through here, you'll see that the forces are such that the projection of the force in the tangential direction, let's say the wind force is W, is going to be positive. That means it's doing positive work. That means it's speeding up the bogey. It's speeding up the trolley. And when you get to the other side, now the tangential direction is pointing somewhat downwards, and so is the wind, now pointing downwards. So the projection is going to be positive for the wind on the sail bogey. Again, doing positive work. So this is going to do positive work this entire time as it goes through there. So there's some positive work there, we know that. And then, if you were to take the same 2 points, we can call them anything we want, A and B, and take this dotted path between them, then you're going to have no work. And why would that be? Well, that's because your velocity is in this direction, the tangential direction, along this straight line in the x direction, and your wind is perpendicular to it. Work cannot be done in a direction perpendicular to the direction of travel of your object. Work is only done in the direction of travel of your object. And this is the same thing we've been talking about since we first put vectors into kinematics, right? Since lecture 5, we've been saying that acceleration in the tangential direction speeds you up or slows you down. Then, of course, we said in lecture 6 that forces are what speed you up and slow you down. And therefore, in lecture 7, we said that only the force in the tangential direction is going to speed you up or slow you down. So we've seen all this before. We've done plenty of problems where we cared about that. So in this case, we're going to calculate exactly how much work is done along that path. And that's going to be interesting for 2 reasons. 1, we're going to have to figure out how to write this wind and how that actually works out. And 2, we're going to have to deal with the integral form of the work. So the work is going to be the integral of f dot ds from its original point A to its final point B. And so we have to figure out what that ds is. And we've already said in class, if there is class, that ds is going to be t hat ds, where t hat is, again, the direction of travel. So s is going to be how far along you've gone on that path, and ds is going to be an increment along that path. And it'll be a little more interesting because we're going along this curve, so that ds is going to be equal to r d theta. That's going to make life a little bit easier for us. It's harder if we have to actually write a function for s. So now let's start with the problem-solving process. We always want to do this problem-solving process. The reason why I'm doing these videos and the reason why I do the lectures in class is for the problem-solving process, right? What is going to happen on this video for the problem-solving process? First of all, we have to draw our situation. So we've already said we've got an arc, like so. if we look down here, it says it's a quarter circular section of the railway, and all of the action is going to go along this perpendicular line. I'm going to choose it to be perpendicular. You could put it in the x direction, I put it in the y direction. That's all taste. Quarter circular thing, it's traveling 90 degrees here. That means this is perpendicular, that's a right angle. So this is plus 45 degrees, or probably better yet, plus pi over 4. And this is minus 45 degrees. This radius here is r, and so we'll go along that path. That's our path for calculating the work to show that it's non-zero. The actual function for the wind is going to be positive on the left-hand side and negative on the right-hand side. After we've gone a distance r, which is farther than here, so this is only about 70% of the way to this number, the wind will be with a strength W0. So this point is r, and that's W0. And furthermore, at this point here in the center, the wind is 0, and it's a linear change. And so you end up with a wind force as a function of x that looks like this. And if this is r, this is W0. This is the wind force, not the work, and I think that's all we need to know. Let's see, yeah, we talked about all the things that were given, basically. So we should write what we're given. Let's see, we've got a wind force with a force constant of what? W0, I just said. Right down here, W0. And a range constant of r, right? So our wind vector is W0 over r times x. That means that at 0, this will be 0, which is what we want in the center here. And at r, x over r is 1, so the magnitude of the force will be W0. And to make it positive, when x is negative, we have to put a minus sign on that y-hat direction. So that's going to be our wind force when we come to it later on. What else do we have? We have a track. We don't know anything about the velocity of the sail bogey, we just know about the force. So this is a little different from some of the other things we've done with wind. This is just to make a point. We're going to say this is what our wind force is. Our track is going to have a radius, r, and it's going to start and stop at plus or minus pi over 4. So what am I left with? I need to find something. What I want to find is the work done by the wind. And that's going to have a symbol W, because I like W. Okay, so that gets us through the setup. Now we need to analyze the physics. So we're done with the situation. We want to analyze the actual physics. So what do we have? Well, we have that we need to do work, and our equation for work is going to be W is equal to the integral from A to B, which we talked about before, of F dot ds. This is a general equation to go with the work. The representation for work should still be a free body diagram, because we have to integrate over a force. And we should use a free body diagram over here off to the side. We want to do that because when we draw our free body diagram, we want to do x and y, I think. When I come over here, what I'd like to do is I'd like to figure out what's driving this and stuff like that. So one thing we know is down here, we've got a normal force pushing towards the center from the rails on the bogey, a wind force pushing up. So we've got a wind force coming up there. And then we have along this tangential direction an ms double dot, which is the net force, right? The acceleration along the rails. So you can see from this that the n direction and the w direction are not parallel. But if we were to draw our free body diagram right there along that y-axis, then what would happen? N and w would be parallel, and then we wouldn't understand the problem quite as well. There'd be a problem how we set things up, possibly, depending on what we did. Okay, so now I've cleared that up a little bit. We need to work on the plan. So what do we need with the plan? Well, we need to start, 1, with the definition of work to find work. There are only 2 things we can use to find work. One is the definition of work, and the other is the work energy theorem. We don't know anything about the velocity, we don't know anything about the kinetic energy, and we don't really have any prospects for finding the velocity in this problem. So we have to use the definition of work. But the problem with using the definition of work is that there are many ways to write it, from the simplified one, which is just work equals force times distance, to the one we showed earlier, which is the work is the integral along the path of the force. And that's actually what we have to use. And we have to use that because we have a curved path and we have a variable force. So with both of those complications, we have to do this. I'm going to write the limits of integration as negative pi over 4 to pi over 4. Hopefully that's sufficient. Technically, I probably should write it as r of pi over 4 or s of pi over 4 or something like that. But I think that just makes things a little more confusing for now. So let's not do that. Then we need to write this is going to be the wind force that we've talked about earlier, dotted with the line element, the small increment along this path, including both the magnitude and the distance that we take as we go along the track. So tracking symbols, W is a target variable. Let's see, what do we have over here? We have the wind force and we have the line element. We don't know either of these. We need to get some sort of expression for both of these. So that's something unknown that we find later. We love to do that. So the next piece of our puzzle could either be the wind force or the line element. So we're going to go with the line element. So we already talked about the definition of that line element. And the definition of that line element is ds is equal to the tangential direction, in this case as a function of theta, times the size of that little element as it's going along. We care about this as a function of theta, so that's r d theta. So it's a little tiny increment of theta at distance r away from the center of this circle, so it's r times d theta. So we were looking for this little guy, not the tangential direction. We need to figure out how to write the tangential direction. R we know, and d theta we don't actually have to know. D theta is going to be integrated out. If you really want, you can give it a little x. It's going to go away. Okay, then we need to find this tangential direction. We'll find that with the definition of the normal direction. Maybe I should call it orthonormal bases. So remember when we talked about the normal direction, it was n hat is equal to z hat cross t hat. Or actually, the normal direction is equal to the binormal direction cross the tangential direction. But because this is in the xy plane, the binormal direction is z hat. It's the direction perpendicular to the other two directions. So we're good with that. Now we have to do something to find the tangential direction with this. And the easiest way to do this is to cycle. So we know that z hat is going to be equal to t hat cross n hat. These are still all cyclic, right? nzt, n, then z, then t. That doesn't give us t, that gives us z. And we already know z because it's an absolute direction. So t hat is going to be n cross z. And rather than call it the normal direction, what we're going to call it is the radial direction today, because it's the radius of this circle. So we're going to say t hat is equal to n cross z. Remember, these form an orthonormal coordinate system. That's why we're allowed to do that. But they're all relative directions, so we don't assume that we know what the directions are. We have to find them. So what we're going to have to do is we'll have to find that normal direction, that radial direction. And we can find that radial direction with, well, we can call it many, many things if we like. We could call it trigonometry. Trigonometry is one way to talk about it. Probably geometric construction would be okay. So let's call it n, this radial direction, is equal to, let's see, in the x direction, we're coming from theta equals 0 in the positive y direction. So x direction has to be sine theta, and the y direction is going to be cosine theta. Okay, so that's all right. So we were looking for n, and we're going to integrate out the thetas. So we can put little boxes with check marks, likely cancels. When we integrate out, this guy is going to cancel out these guys. Okay, so that looks like a dead end. I think we got to the end of the line element track. So if we've gotten everything down from that line element, there aren't any more question marks from the branch, and the branch happens in equation 1. That means we have to go back to what we have. So let's just check. So n we have, so that's in 3. T we have, that's in 2. And ds we have, that's in 1. In 2 and 3, there aren't any other question marks. So the next thing we solve has to be W because that's the only question mark left. We have to find the wind force. So we're going to do that with algebraic construction. Okay, so then W is going to equal, we said way over off to the side here, a little bit farther than this, if we continue the circle out to R, that's going to be W naught. It's going to be equal to W naught times X over R, so that it's 0 here at the y-axis, and it's W naught, or in this case minus W naught, at a distance R from the y-axis. And then we need a minus y hat. And remember, the minus y hat kept it positive on the negative side of the y-axis and negative on the positive side of the y-axis. So we already discussed how to build that, and then we built it again, just for fun. And we need that one, we need that one. We don't know what x is, and we know what y is because y is an absolute coordinate, just like z is an absolute coordinate. We don't need to figure anything out about absolute coordinates. 6, we need to find x, so let's use vector decomposition. And that is just going to be, let's see, the radius vector is equal to x hat plus y hat. I don't anticipate needing any y's. X is what we were looking for. So an arrow at x, and it's the radius vector that we don't know. So we don't have an expression for the radius vector r, our arrow. So we have to find something with that in terms of things we already know to get through this. So we've gotten rid of that x. Now we need 7. We'll use the definition of vectors. And remember what we said was a vector, like r, is equal to a magnitude, in this case the radius of the circle, big R, times a direction, in this case the normal direction. R is a point along this circle. It's a position along that circle from the origin to the circle. Everywhere along that circle is a distance r away, right? So we get the little box. We're looking for the r, that's an arrow. And the direction pointing out of the circle is the normal direction that we found up there. That gets a check mark. So there aren't any question marks left. We got that one, and so we're done with the plan. Being done with the plan means we can do the math. Obviously, there's not a lot of math in physics. Most of it's just substituting things in and rearranging them. But it still has to be done. So let's start with A. What do we want? We want to substitute. What should we substitute? Well, let's try to get 7 in a similar form to 6. So 6 is r equals x plus y, x hat plus y hat. It would be nice to have another expression where r is something times x plus something times y, something times x hat plus something times y hat. So we happen to have a definition of that normal vector up here in number 4, so if we substitute 4 into 7, we've used both of those, we have r is equal to the radius vector times sine theta in the x hat direction. That's the sort of thing that confuses people, plus r cosine theta in the y hat direction. That's a similar form to 6. So if we want to find x, we can equate 6 and a. We want to say that this x is equal to something over here. So this component of r, the x component here, is going to be equal to the x component over here. So x is equal to r sine theta. We've used that 6. Actually, we've also used the a. So now what we wanted to do is substitute that x into 5. So then we'll have w as a function of theta, so we'll be able to integrate that theta out. So let's substitute b into 5. So we'll just take that x and plug it in there. The r's cancel, so we just end up with the wind force is equal to its magnitude times the sine of theta in the minus y hat direction. Seems reasonable. We have to use each one of these steps that we've had in the plan and in the execution, except for the last one, obviously. So that's why I'm crossing them out. That's why I ask you to list them on the problem-solving template. So then, here we are, and there's no more things we can do with w until we plug it into the work equation, but we don't have ds done yet. So let's go down the other path. So now we've done the wind path. Let's now do the line element path and get an expression for the line element. So let's substitute 4 into 3. Like I said, we can use the same thing twice. We're going to substitute 4 into 3, and that will give us this tangential direction that we can use in number 2. That's just t hat is equal to the cross product of r cross z, or the normal direction times the z direction, the normal direction to the track. So let's see what we have. That would mean we have sine theta x cross z plus cosine theta y cross z. So x cross z, we skip the y, so that's a negative sign. So t hat is equal to something times minus sine theta y hat. And then y cross z, that's sequential, right? That's cyclical. So that means that y cross z is positive. That means we have a positive cosine theta in the x direction. So t hat is equal to cosine theta x plus sine theta y. Good. We've already crossed both of those off. Now we have to put that into our line element. So I'll put that into the line element. We'll substitute into 2. So that's ds is equal to t hat, which is complicated, cosine theta x hat plus sine theta y hat times r times d theta. Just enough room. Awesome. So we put all that stuff together and we're ready to plug both of these, C and E, into 1. All right, so that means our work is going to be equal to the integral from minus pi over 4 to pi over 4 of W, which is C, which is W naught sine theta, times the y hat, dotted in with the ds, which has an x hat component, which we can now ignore because x dot y is 0, and the sine theta y hat. So we have a sine squared theta, and y hat dot y hat is 1, and we have a minus here and a minus there. That's also 1. Then we have an r. So we have w naught r sine squared theta d theta. So all we have to do is the integral of sine squared theta d theta, because w naught and r are constants. So we integrate. And that integral, if you do it, is pi minus 2 over 4. And we have the constant w naught over r. So that is the amount of work, which is not 0. Pi minus 2 does not equal 0, except in Indiana. So that gets us done with the execution. We've done all the math. This is our answer, and we want to check it. When we do our checking, that's the answer we're checking. Okay. First thing we check is the symbols. On the right-hand side of this equation, we have to know everything. So we've got 2 things we can know. We can either know things that are in the givens, or things that are universal constants, things that we can assume, things like the gravitational acceleration, the density of water, and so on. So let's look at these symbols. Well, pi, 2, and 4 are not really symbols, they're numbers. We don't have to check numbers. W naught and r, those are both symbols. So let's look at W naught. W naught is up here in the givens, so we put W naught there. R is up here in the givens twice, so it's here. An interesting thing for you to try to figure out would be if the range constant and the radius were different, how would the answer differ? Let's see, there are no more symbols in our answer, so we don't have any universals, we don't have any excess, so the answer at least is reasonable as far as the symbols are concerned. The next thing we want to check in this answer here is the dimensions. So first we want the dimensions of work. The units of work are Newton meters. A Newton meter is the same units as a joule. Joule is energy. Energy is mass, length squared, t to the minus 2. What do we have? Well, we have W naught R. That's the units of W naught times the units of R. W naught is a force. That's mLt to the minus 2. R is a distance. That's an L. So we multiply those together. We have mL squared t to the minus 2. And those two match. So on that dimension as well, this is a reasonable answer. That doesn't mean it's right. It means it's reasonable. We have one other reasonability check, and that's what we'd expect to have happen here. So we expect, for example, that if the wind is going to provide work to the system, then the stronger the wind, the more work is done to it. A stronger wind in this case would have a larger force constant. So if the force constant was larger, then we should have a larger work. So is that what we get when we look at this answer? What happens to W when W naught increases? Well, when W naught increases, you get a larger number on the right-hand side. So W increases as W naught increases. That's exactly what we said we should expect. So it's also reasonable on that level. So the answer is reasonable. We don't know if it's right. We only know if it's reasonable. But that's what we want to do in the checking part, is just see that it's a reasonable answer. So I think that was a fairly informative problem. The really informative parts are 1, the construction of the line element. 2, finding the tangential direction from the normal direction. And 3, constructing the wind force. Hopefully you're good enough with constructing the wind force. All the other things you've basically done, right? You just need to learn how to construct the line element for the line integral, and you're perfectly good. There's one homework problem. There's one homework problem where you do have to construct your line element, or you should have to construct your line element. And so hopefully that'll be useful. Probably won't see this use of the normal direction again in this class, but it would be good to remember that's the sort of thing that you have to do when you have to do something like that in the future. The algebraic construction you've done many, many times already, and hopefully you're getting used to that by now. I had a fun time with this problem. I love that sail bogey. I bet you love that sail bogey. And so, when I see you again, I want you to have a sail bogey t-shirt. Bye now.